The Baeyer-Villiger oxidation takes an aldehyde or a ketone, treats it with a peroxy acid. Most acids in organic chemistry are carboxylic acids, and those look like this. You have a carbonyl with an alcohol on one side. So that's a normal carboxylic acid. The prefix per means a lot. Like if something is perfect, the fect means done. It's really done. It's a lot done. It's like totally done. If you try to do anything more to it, you couldn't. It's perfect already. So the per means a lot. And if you have a peroxy acid, then it's like having this acid here, but with an extra oxygen in it. And you'll notice there are 3 oxygens there, so 1 on the top and 2 sort of on the side. And one way that that's often written is R, so that's like these carbons. And then you have the O3, oops, and then the H. So that's just an abbreviated way of writing that. We've seen these before. MCPBA was metachloroperoxy benzoic acid. We've used them to make epoxides from alkenes, for example. Now, in this case, they can also react with aldehydes and ketones, and what they end up doing is they take one of the carbons right next door to the ketone, and they stick an oxygen in between. So that carbon is still there, but they stick one of their oxygens in between here. And they end up turning these aldehydes, or in this case, what I've drawn as a ketone, they turn them into something called an ester. So an ester is when you have the carbonyl, and then on one side you have an ether. So a carbonyl with an ether right next to it is an ester. And that's what these Baeyer-Villiger oxidations do. And you can remember it's an oxidation because you're forming new bonds to oxygen. You're increasing the number of bonds to oxygen in the molecule. And that's hinted at by the huge number of oxygens that are in your peroxy acid reagent. Okay, let's take a look at how the mechanism for this happens, and then we'll just focus on just a couple details, like one minor detail. So for the first step for this, you can think in you want to think in terms of the arrow pushing patterns. The mechanism for this is not long. It's really just 3 steps. But you get to see sort of the similarities and differences between the previous mechanisms we've done. The 3 steps are nucleophilic attack. That should seem really familiar. After all, we have this carbonyl, and a carbonyl is famous for its electrophilic carbon. So a nucleophile can attack that. Then we will have proton transfer. Again, this should seem very familiar because after you have nucleophilic attack with a neutral molecule, and that's all we have here, you create charges. If everything's neutral to begin with, then when it starts reacting, you get a charge. Then you have to do a proton transfer to help minimize that charge. The last step here is one of the reasons that I think this is an interesting mechanism. It's a curved arrow pattern that you don't get to see too often. And so when it's used, even though it's very prevalent in living things and in organic mechanisms in general, and so sometimes when it's involved in a reaction, the reaction will look really foreign. So it's nice to have at least some context, to build some context, to have had some experience in seeing these rearrangements. The only rearrangement that you would have seen frequently up until this point would have been carbocation rearrangements, where a hydrogen with 2 electrons, so that's called a hydride, or a methyl group move over toward a carbocation in order to create a more stable carbocation. This is not going to be a carbocation rearrangement, so it's worthwhile taking a look at it. Okay, well, what do these look like? First, you have your molecule. And for us, that will be this ketone. And then you have this peroxy acid. So you'll want to be able to draw that. You can imagine drawing that sort of as an upside down U. So first you have the H, oxygen, and then you can do another oxygen, and then the carbon, and then the carbonyl. So it's sort of like a U, an upside down U, with that RCO3H, and then whatever carbon chain. The carbon chain really doesn't matter here. It's the peroxy part that's going to be doing the reacting. So in this mechanism, the oxygen is slightly negative. These oxygens are slightly negative. And of course the carbonyl carbon is slightly positive. And so one of the oxygens can attack the carbonyl carbon. So that should look really familiar. When that attacks, of course, the pi bond breaks and its electrons snap up onto the oxygen there. They go to the most electronegative place nearby. And it's the pi bond that breaks because the pi bond is weaker than the sigma bond. Pi bonds have interrupted overlap of those p orbitals, whereas sigma bonds are uninterrupted overlap. And so they're stronger bonds. So this is our nucleophilic attack. And after that attack, you get very much what you would suspect. It's the same. The two molecules are just attached now. Otherwise, they look the same. This bond to this oxygen, there's only one bond there. Now the oxygen has 3 lone pairs and a full negative charge. And on the bottom, we have this oxygen, which is bonded to the rest of our sort of U, upside down U shape, and the hydrogen. And you'll notice that this oxygen has 3 bonds, so it has a full positive charge. Okay, well, that oxygen is very unstable with the positive charge. And so to stabilize it, you do a proton transfer. That is our next step here. And the oxygen in the carbonyl ends up stealing this hydrogen, and its electrons go onto the oxygen to stabilize the positive charge. So that is our proton transfer. When we're done with that, we have almost the same molecule, but this hydrogen moves to this oxygen, which now only has 1 lone pair, 3 bonds, so that has a positive charge. And this bonding electrons, those go onto the oxygen there. Okay, so we did a proton transfer. Now is the sort of interesting part. Now is the rearrangement. So that's what we're going to get. Okay, well, this oxygen here is very unstable, and the carbon that it's bonded to is very slightly positive. This carbon is bonded to 2 oxygens, both of which are stealing its electron density, and so the negative oxygen is really attracted to that, and it tries to make a pi bond to it. It uses its lone pairs to make a pi bond. But if that's going to happen, something has to move. Now, this bond between these oxygens and the peroxy acid is very unstable. It's why peroxides in general are so reactive. That bond is so unstable. And compare, single bonds between oxygen are very unstable, unlike single bonds between carbons. It's one of the reasons why carbon is the basis of life. It can form stable bonds to itself. And so we see a contrast in that with this oxygen. This bond is going to break. It moves over. There's a pull on these electrons here toward the positive charge. And so if you sort of think of it, you have 2 things happening at the end of the molecule. The negative charge wants to stabilize. The positive charge wants to stabilize. So the negative charge to stabilize snaps down. The positive charge to stabilize pulls these electrons, tugs them towards it. And this weak bond is stuck in the middle. Well, these electrons follow the pull and go toward this carbon that's losing electron density. And now is the strange part. Now is the rearrangement. One of these bonds to the carbons, those pick themselves up and those move over. And the one that moves over is either, if there's a hydrogen there, the hydrogen will move, because it's so small, it's very easy for it to move. But if it doesn't move, then it will be the carbon that would make the most stable carbocation. Because as it's traveling over, it doesn't have electrons for a hot second, and so it has this sort of carbocation that it needs to stabilize. And so if you look at these, you have this carbon on the right, which is secondary. It's bonded to 2 carbons. This carbon on the left is tertiary. It's bonded to 1, 2, 3 carbons. And so this can handle a positive charge on it for a second better than the less substituted carbon can. So it's going to be the carbon on the left that moves over. It's going to take its electrons and bond itself to that oxygen. That is your rearrangement. Now, the pull, the push, the impetus for that rearrangement is the pressure coming down from that oxygen and the pressure pulling away from these groups over here. Ultimately, it's the charge in the molecule that's forcing this to happen. Okay, so when the dust settles there, you end up with a double bond to this oxygen, so that's this bond there. The carbon on the right has not moved. Now, you still have that oxygen, but it has your carbon branch bonded to the other side of it. And notice, the rest of this is not the most important thing, but what does end up happening there is you get a carboxylic acid, just a normal one. So that's what you end up getting in there. And you'll recognize that that is just a regular carboxylic acid. It's not a peroxy acid. And so that is the mechanism for this particular Baeyer-Villiger oxidation, Baeyer-Villiger oxidation. And you'll notice that you took a ketone, or what was originally a ketone, and you turned it in to an ester. So you have a carbonyl with an ether on one side. So a carbonyl with an ether on one side, that's an ester. Okay, so let's do that process again. We're going to use these same 3 steps: nucleophilic attack, proton transfer, and rearrangement, not carbocation rearrangement. We're going to do it with this molecule here. So, let's get some room. So, draw your aldehyde or ketone. Next to it, we're going to draw our peroxy acid, and you're going to do this sort of as an upside-down V. So hydrogen, then going up an oxygen, and then going up an oxygen, going down a carbon, and then the carbonyl. So the upside-down V, or U, and then you have the carbon chain there. And both of these have lone pairs. Well, the first step is nucleophilic attack. This carbonyl carbon is very positive. It's a strong electrophile. These oxygens are slightly negative. The one in the end is in the least crowded position. And so that attacks the carbonyl carbon. The pi bond breaks. The electrons go on to the carbonyl oxygen. So that is our nucleophilic attack. Now after that happens, you just have these 2 fragments, these 2 molecules connected. Oops. Have that going in that direction. This oxygen only now has 1 bond to it, right? The other one broke. That became a 3rd lone pair on the oxygen, which now has a full negative charge. And bonded to this carbon will be the oxygen of the peroxy acid. Okay, so this oxygen in this middle area is very unstable. It has that positive charge. Positive charge on an electronegative atom is very unstable. And so it quickly tosses off its proton, its hydrogen, to help stabilize that. And the closest thing nearby that can handle that is the carbonyl oxygen. And you can remember that that can handle that well because of the resonance structure that you get, that has. There's a resonance structure here where the oxygen has a full negative charge. So it attacks that, and we saw that in the mechanism for the first video we made for the mechanism for acetal formation. So the carbonyl oxygen attacks that hydrogen, the electrons go back onto the oxygen, so that's our proton transfer. And then what we have is basically the same molecule, but with the hydrogen moved. So this is not a lone pair anymore. It's going to be a bond. It's going to be a bond to this hydrogen. Now that oxygen has 3 bonds, so it has a full positive charge. And what was a bond will be a lone pair here. And that takes care of the charge there. Okay, well, that oxygen is now more comfortable, but the molecule itself feels a lot of pressure. And the ends, we have a full negative charge, and that full negative charge is right next to a slightly positive carbon, a carbon that's bonded to 2 different oxygens. And on the other side, we have a full positive charge on an oxygen, which is an electronegative atom and prefers to have a negative charge. So we have those 2 things pushing the electrons generally in this direction. The oxygen snaps down and tries to form a bond to that positive carbon. And this oxygen pulls on these electrons to help stabilize its positive charge. Well, that means this carbon is now losing electron density, and this very weak bond between the oxygens moves over to help stabilize that. But now this oxygen is in the middle of a vise. It's losing electrons on one side, it's feeling pressure getting pushed towards it on the other side, and to help stabilize it, one of these things bonded to this carbon with the positive charge moves over. Right, that carbon already has 4 bonds. If the oxygen on top is going to try to make a new bond to it, something has to move over. And what moves over is either a hydrogen if there is one there. If there is one there, then the hydrogen will move over because it's very small, so it's easy to make that travel. But if it weren't a hydrogen, then it'll be the most stable carbocation that can move over. Well, there is a hydrogen here, and so the hydrogen takes its electrons and moves onto the oxygen, and that is a rearrangement. This whole process, that whole third process, is a rearrangement. It's all one molecule. It's just things are attaching differently. Things are moving around on it. And so what you end up with there is this carbon chain. Now there's a double bond to the oxygen. You have a branch going down. But instead of just going straight to the hydrogen, it goes to the oxygen and then the hydrogen. So the oxygen inserts itself there. And what we have left with on the other side is just a carboxylic acid. That oxygen double bonded to a carbon, single bonded to an OH. And so in this case, we took an aldehyde and we turned it into a carboxylic acid by doing this Baeyer-Villiger oxidation. Okay, let's see the same mechanism again with a different carbon backbone, just to help reinforce this. And this will be our last of the Baeyer-Villiger oxidation mechanisms that we get to see. So we're going to do these 3 steps again. First, draw your aldehyde or ketone. In this case, they're giving us a ketone. And then draw your peroxy acid. That's that upside down U. Start with a hydrogen going up. We have an oxygen over, oxygen down, carbon, and then the carbonyl, and then an R group. So that is our peroxy acid. Now the carbonyl carbon here is very slightly positive because it's losing a lot of electron density to that oxygen. So it's a very tempting electrophile. And this oxygen on the end is slightly negative, and it's the least crowded oxygen because it only has a hydrogen, which is a small atom, on one side. So that can swoop in, attack the carbonyl carbon, the pi bond breaks, and the electrons go to the most electronegative thing nearby, which is that oxygen. So that is a nucleophilic attack. What we have after that nucleophilic attack, let me just make more room. So what we have after that nucleophilic attack is that same 5-membered ring with all its accoutrements, all of its branches on it. Now we only have one bond to this oxygen here, which has 3 lone pairs and a full negative charge. And in the other direction, we have this whole molecule. So this oxygen with the hydrogen, also bonded to another oxygen, bonded to the carbon and the carbonyl, and then the R group. So notice this oxygen here has 3 bonds, so it has a full positive charge. Well, that's really unstable for an oxygen, and so this oxygen to the right steals that hydrogen, and the electrons go back onto the other oxygen to stabilize it, and it's able to do that because it can stabilize the charge that comes with it through resonance. There's another resonance structure there. Okay, well that leaves us with a very similar structure. We don't have this positive charge anymore because this oxygen gets electrons all for itself. This lone pair turns into a bond to the hydrogen. Now that oxygen has 3 bonds, so it has a full positive charge. Okay, so this second step that we did was a proton transfer. Well, now there's a flow of electrons that wants to happen in this molecule. You have a lot of electrons building up here. You have a need for electrons on the other side. And so that carbon on the one end feels the slightly positive charge on this carbon that's bonded to 2 oxygens. Oops. So the electrons snap down and create a pi bond. At the same time, on the other end, this oxygen can't handle the positive charge. It steals electrons for itself. That creates a cascade. This weak bond in the middle can't handle the pressure. It breaks and goes to the carbon that's losing electrons. So now, something has to give. This carbon has 4 bonds. The oxygen is trying to make a new one, so something has to move over. And the thing that moves over is one of these carbons. Now it'll either be the carbon on the left or the carbon on the right. There is no hydrogen bonded to this carbon in the middle. The hydrogen would move over the fastest because it's so small, it can move more easily. But since there's no hydrogen bonded to this carbon in the middle, we have to move a carbon branch over. And we're going to move the carbon branch over that could handle a positive charge for the brief time it takes to move best. Well, that is the more substituted carbon. This carbon on the right is bonded to 4 carbons, the one on the left is bonded to 3, so this can handle a positive charge better. So it's the one on the right that ends up moving over. So it takes its electrons and it attaches to that carbon. So that's a rearrangement. That would be maybe the most uncomfortable part of this whole mechanism. The new thing, but it's new now. You want to get used to it now so that when you see it in large biological reactions, you have this context already in your mind. You've seen it in this Baeyer-Villiger oxidation before. So when that happens, notice what happens to our ring. First of all, leaving the molecule is this whole thing. That's gone. That leaves as a carboxylic acid. That's what that turns into. once you move those electrons around according to those curved arrows. Now what you have left, you have this double bond to this oxygen here. The carbon next door still has the methyl group. Now let's number these. This will be carbon number 1. Well, let's do this. So this will be carbon number 1. This will be 2, 3, 4, and 5. Okay, so carbon number 1, 2, 3, 4, 5, and in between 5 and 1 will go this oxygen. So we know that that oxygen was always attached to carbon number 1. That's this bond right here. But now 5 is going to be bonded to it on the other side. So you end up with a really interesting molecule. First of all, you've changed the size of the ring. That's kind of magical. And the other thing you've ended up with is a sort of ester in a ring. So you have this carbon double bonded to oxygen with an ether on one side, but it's in a ring. That's a special molecule that has its own name. It's called a lactone. It has some interesting chemistry. If you Google lactone, you'll find some interesting stuff. But you can form these lactones by doing this Baeyer-Villiger oxidation with a ketone in a ring. So here we've done some examples of these Baeyer-Villiger oxidations, which are just 3 steps. So much less than something like acetal formation, which is 7 steps. And they're familiar. Nucleophilic attack and proton transfer, that's happened in every mechanism we've done so far with aldehydes and ketones. And then we get to form a new context in our minds. We get to see rearrangements, these sort of not carbocation rearrangements, but rearrangements of other types of atoms. Now is a time when you get to build up the ability to recognize those, to feel comfortable with those, so that when you see them in biological reactions, it fits into a context that you already have in your mind. So that is the Baeyer-Villiger oxidation, inserting an oxygen in between a carbon and a carbon.